but I'm going to start QEMU, right, which is one of these PC emulators, and it's configured to, have its file system is stored in fs.image. The x86 is actually the kernel, and M specifies the number of megabytes, and we're going to run the 5 to 12 megabyte, and we're set it up basically so that you can actually attach GDB to it, so it's easy to debug it. Right? This is the this is sort of the intelligent form of like a hardware oscilloscope. So you can actually poke at the system, because otherwise you could not be able to do that if we were not emulating. Okay, so start it up. QEMU, you've seen this a long times up. I'm going to start the debugger. One of the things just first to point out, how many people run on Macs? All right, so if you're running a Mac, you can't use the GDB that's on the Mac because Mac OS has a different way of laying out their binary files than we're using. We're using ELF. Mac has its own plan, and so you have to have cross-compiled applications to be able to do this on Mac. So I have a cross-compiled GDB that is set up, and I'm going to break OX700. These are like one of these magic constants. It turns out, like by agreement, that the BIOS. So the first thing that happens actually when you press on/off is that the BIOS runs, and the BIOS is stored in some ROM, which is a read-only memory somewhere on the board, and the BIOS is basically an whole operating system itself. It actually has interrupts, all kinds of stuff that it does. It's a very complex program. We don't have the source code. We could look at the source code, but we don't. And basically, it configures sort of the whole PC platform. Pokes at the north bridge, the south bridge, whatever, makes everything behave like a hardware platform, so that subsequent software can use it. Okay. And by agreement, so the BIOS ships basically with your computer, right, with the hardware. And then by agreement, it will start executing instructions at address 7C00. And so that's where it's going to be running. And so your bootloader basically has to be there. And that's the instruction that starts. And that will then load the kernel itself. And there's a lot of separation, correct, between software vendors and hardware vendors, right? Because you can run different operating systems on the same platform as long as they all start loading, because they know that every PC will start executing instructions at 7C00. Okay. All right, so let's set the breakpoint. Now the other thing I probably want to do is the makefile or the GB has to be configured to actually look at the x86 kernel as the JOS kernel, but I really want to look at the bootloader, right, which is basically a completely separate program from the kernel itself, from the operating system itself. And so I'm going to load the I think it is. There's a good name. Actually,
yes.
No. This is the x86 source code. Yes, that's what I want.
Yes, boot vault.
Thank you. I did it for a lecture and then I forgot again. Yes. All right, so go. Now we're good. So debugger, we're running. So we're going to start, continue, and boom, we're stopping. We have a breakpoint at 7C00. So this is the first instruction that's being executed by the bootloader. And we said something on the left. We said booting from hard disk. So it sort of knows a little bit about there's some agreements about what the BIOS, where it gets the bootloader from. It actually comes from the hard disk, and so loaded out. The BIOS loaded that into memory, and now it actually is executing your first instruction to the bootloader. Okay. And so the bootloader actually is, if you want to look at it, actually on sheet 82 of the x86 booklet. And this piece of code, the bootloader between, as I said before, between JOS and x86 are basically identical. So it's one of the few places where when you're looking at code where they're the same. How many people actually have looked at the JAWS bootloader yet? A couple. Okay, good. Well, if you have any remaining questions after studying the code, now is the time. So the first thing you see that the bootloader does is this instruction CLI, which we haven't talked about it. Basically, it says clear interrupts. This basically tells the x86 not to take interrupts. Why do we want to do that? Why is that the first instruction that we're going to? The answer is very simple, but we're not set up to take interrupts yet, right? We haven't programmed the hardware to do anything with interrupts yet, and so we better not get them because otherwise something bad happens. And so it turns out, like to take interrupts, you have to set up a whole bunch of infrastructure that we haven't done. And if you have not set up the instruction, basically you get a triple fault. Your hardware just stop working and like blue screen. And so it's important to, first thing to do is clear interrupts so that we don't actually have to worry about that. And at some point later, presumably, once the operating system is running and has everything set up, we're going to enable interrupts. Okay? So, let's look at the, so that was the instruction 8212. Now we can sort of single step, correct, through the bootloader and see what it does. So the first thing is an X or W. And so why is the W here? Or not a long or a wide? And why is it AX instead of maybe AL or AD or, yeah, go ahead.
So you're still in 16-bit mode.
Yeah, so what happens, the bootloader sort of has to nourish, the PC platform from like being an 886 processor from the 1980s to, sort of modern PC, from this age. And because it's all about backwards compatible, correct? It had to be the case that old programs worked on new hardware, so the old hardware has first to pretend to be, new hardware has to pretend to be old hardware first, so it can run those as old programs. Okay? It's binary compatible, like no change necessary. And so what does this instruction do? XOR, why is this? This is sort of a standard idiom, but if you have never seen it, what is the effect of this?
There's the value of AX.
Yeah, it basically sets AX to 0. It's a clever way of setting AX to 0, involving only registers. No constants necessary. Okay? So the same thing here. Yeah, so it sets up some second selectors, right? And these are the things, these offsets, to form a 20-bit address, and we're just setting all those 4 bits that we're going to be using. We're only going to set them to 0, so basically we can ignore them. And so it means that we can't reference 20 bits, 22 to the power 22, but we're only in the bootloader. We don't care about so much memory. Okay, okay, then this is something completely, this is like typical operating systems. Everything's supposed to be clean, but then it isn't. And because this has to do with the thing that certain PCs, when we're going from 1 megabyte to 2 megabyte, remember that like 1 megabyte was basically everything you had ever supposed to have, right? And then extended memory happened. But so when extended memory happened, we went to 2 megabyte. But then you need more bits, and you need 21 bits to do a computed address. It means somewhere that it needs to be the 21st address line. But you also want to run on the old hardware, and so you have to do a little bit of work here to get past that, and which is completely boring. So it's just all it has to do with backwards compatibility. So let's just skip it.
Actually, the history of this is really amusing.
Okay,
If you want to find out, you can ask me about it. In terms of practicality for present day, it's completely irrelevant.
I guess it waits a little while. Hopefully soon we're ready for it. Let me double check. Yeah. 60. Okay, great. So we went through that loop. Apparently we're waiting for something for the platform to tell us. Actually, sort of very similar to that loop that we saw in that little driver. That happened. And now the first thing we're going to do is load GDT. And this is the global descriptor table, which we're also mostly going to try to ignore. And if you look at it, it's defined actually at the bottom of page sheet 82. There's a GDT colon and GDT's descriptor. And we're not going to decode it right now, but if you decode this, you'll find that basically what it does, it just tells the hardware to map address 0 to address 0, 1 megabyte to 1 megabyte, and so it's been one-to-one mapping. So there's a complicated set of instructions to set up a one-to-one mapping. So basically it doesn't do anything. And again, this is sort of to nourish the hardware along so that actually we can use it. In particular, what it does, it actually sets a particular bit, a protection enable bit. And the reason we're going to do this is because we want to switch from what's called real mode, this is like X8, there's 886, to protected mode, which is a 286. And so we're going to, in the 286, there's 32-bit instructions. And so we're going to switch, two things at the same time. We're going to go from 16 bits to 32 bits, and we're going to go from real mode to protected mode. Forget what protected mode means. They're totally not important. And with that, these instructions can deal exactly with this, that particular problem. We see, we set the enable bit. So what we're going to do is we're going to use the descriptor. Once protected mode means we're actually using this GDT, the global descriptor table. And there's some protection bits in it. But as I said, we won't care much about it. Robert will talk a little bit about it on Wednesday. We enable the control register 0. We set that flag into the control register 0, and that enables the protected mode. Nothing really happens at this point yet, but then we do a long jump. And this is a long jump because we're going to use it, use a logical address, and we're going to long jump to whatever start 32. And that turns out to be compiled, assembled as 32-bit instructions. And that happens because we put in that dot code 32, which told the assembler now use 32-bit instructions. And you will see, again, there's this great. See that suddenly QEMU figured out the target architecture is now an i386. So it moved from being an 886 to a 386. Then it sets up a couple more segment selectors. And remember, the segment registers are used as selectors, as indices later on 386 instead of offset. And so it does that. Again, not very important because we're going to mostly ignore it, but it will show up a couple places. Where are we now? Zero segment. Okay, so there's a bunch of registers. GS, not particularly important. This is important. We're going to set up the stack pointer, right? We want to call C code and have functions, and so we want to get into C code as quickly as possible. But C code, needs stack pointers, right? We saw that in a bunch of things. So we need to set up. So we set $start to ESP, and then why is that a good idea? So where's the stack pointer pointing to? What address is in it? Yeah, 7C00. Does that seem dangerous to you? Or? Or not? Remember, if the physical memory layout, whatever, somewhere there's 7C00, right? And here's where apparently, here's our instructions that we're executing, the instructions that we're executing, correct? And we print out, if you do info registers, correct? You'll see that EIP is 07C43, right? Which makes sense because we have executed a bunch of instructions since 7C00. Okay? We'll be doing this a lot, looking at the registers and sort of seeing what actually is going on. So it's actually worthwhile looking at. So you see the 32-bit registers, we see EIP, we see ESP. We're having a single step one more time. And look at info registers. Boom, see, ESP points to 7C00. It's just right here. So what is going to happen when the next instruction, correct, as we know, this is a call instruction, correct? Call boot main. What's that going to do? Sorry? Yeah, so it's going to load boot main, the address of boot main into EIP, but it's first going to push the return address, correct, onto the stack. All right, so where's that going to be sitting? Is that going to overwrite our first instruction? Or not? Stack goes down. Very good. This is very crucial. Actually, it's going to go. It's going to store some value here, correct? And what value is going to be stored here? whatever the instruction is after, you know, the call main, which is generally EIP, well, some 7C48 plus whatever in the number of bytes, you know, length of the call instruction, right, or the coding of the call instruction. So it's going to be, the next instruction after the call main was, boot main is going to be move W, correct? Hopefully we never get there, right? Because our plan is going to be that we're going to go to boot main is going to do a whole bunch of other stuff, and we're never hopefully going to return here, ever. But, you know, hard reduction. So some EIP is saved here, and then we're going to call boot main. Right? So let's go call boot main. So instruction, boom. We're now in C code. On page, on sheet 83, you see the call boot main, and we're in nice, clean C code. Right? But, you know, we're looking at the instructions, the assembly instructions. So we'll see the first thing that actually going to happen is only is whatever, we're going to run the epilogue, the prologue, right, of whatever GCC has generated. Okay, so we see a couple instructions. Let's do that. And you see the first is a common sequence here, correct? Move ESP to EBP. What is it doing here? Sending up the base pointer register correctly, right? It's not in the C code, correct? But it is in the, you know, the compiler is generated for us. Okay, so then we have a base pointer to refer to. And we can look at this now. Right? Can you see it? You can see that. Almost done. We'll see that basically, you know, the ESP is 7B F8, correct? It's indeed below that 7C00. And you see that EBP is still 0 because I haven't executed the instruction yet. Oops, again. And hopefully there's something, yeah, see the EBP is now equal to the same value that's actually was pointing here, correct? Okay, and so we're going to single step a couple instructions, and you know, we're basically saving some registers, et cetera, until we get to the point that we're going to actually run real C code, correct? Which is going to be that instruction within somewhere this megabyte $100 is going to be loaded. Let me see if I can push here. Okay, we're actually jumping immediately to the read segment because now the code that we're looking at is slightly, it's not the straight, you know, dumb compiled code. Okay, but I'm running out of time, so I'm going to stop here. But basically, we're in C code already, and the bootloader is not done yet. Right? We haven't loaded JOS yet, nor that we have loaded XP6. But really, what's happening, if you look at that couple lines of code, the only thing it's going to do is going to load some blocks from the disk that actually contain JOS or XP6, and then it's going to jump into it. Okay? But we'll zoom on that story on Wednesday.